Hi everyone, can you hear me? Does the mic work? Okay. Right. Um, okay everyone, hi, thanks for attending this training session and I hope you enjoyed the sessions so far. My name is Nicolas, to those you. I'm a machine learning engineer at the Cyprus Institute, so I've joined about a year ago. I have a master's in artificial intelligence, so I'll be talking a bit about data science and specifically text processing. So this session is about on the timetable. It says that this session is an hour and a half, but I'm pretty sure we'll finish a bit earlier. Also, this is the last session of the day, so we won't have any conflicts. I hope you enjoyed the sessions so far. So I'm sure that Nikos and Valeria today covered a lot of topics, and it was quite technical. So I'll try not going really deep into the technical stuff. At least some things I can't skip, but I'll try keeping it lightweight for today. Yeah, you can see my screen. So I'm not sure if you guys have seen this repository. I'll share it in the chat. So you can access all of the stuff from here, actually, after the session as well. So if you just go to the chat and open the link, and you'll be able to see this repository that I'm sharing now. So if you just go to day 3, you'll be able to see the notebooks for the 3 sessions, today's sessions here. And you can just click at the opening collab button in this last session here. And this will just take you to the notebook that we'll be using for today. So if you click here, it should take you to the notebook. So I know that you've used notebooks for the other sessions as well. So I guess my colleagues already told you that in order to efficiently run this, you should save a copy to your drive and run that, because otherwise we'll have a conflict in the run times. But this is only for the people that want to be, actively running stuff while I also run the notebook here. For the rest of you, you can just look at the presentation and run it later on in your own time. So Google Colab is a really nice tool for things like that, for sharing code, for running experiments. It's a free service offered by Google. It gives you some runtime on some Google GPUs if you want to try machine learning applications and things like that. And it's also really nice because it plays well with Google Drive, so you can store things to your drive and access them through there. But it also gives you some temporary storage. So here we won't be using the Google Drive at all. We'll be just downloading some things temporarily from the web. So let's jump into today's session. As most of you already know, we'll be talking about text processing. So, okay, text processing in the context of data science has to do with textual data, okay? Today, you heard a lot about structured data, so tabular data, which are just numbers from what I heard, and about time series as well. In some other training sessions, we talked about visual data as well, so images, videos, things like that. The umbrella of data science is really wide. It covers a lot of things. You would need ages to, understand in depth all of the concepts in data science. But I believe that text processing is extremely useful, because nowadays you have textual data everywhere. So Facebook, let's say, or Amazon or Twitter use loads and loads of text on a daily basis, and you need to know some basic methods to be able to process those. Okay. So when we talk about text processing in the context of data science, okay, we actually talk about natural language processing, or NLP. And I'm pretty sure that most of you heard this term sometime, especially recently, because we have like really big state-of-the-art models right now in NLP. I'm pretty sure you heard about this model developed by Google that supposedly became sentient and they needed to shut it down. So that's actually an NLP model based on some really complex mathematical foundations. But NLP in its essence is an intersection, if you may, between linguistics, so the study of human language, and that has nothing to do with computer science at this stage. But it also intersects with computer science and artificial intelligence. So when we say artificial intelligence, we mainly mean machine learning, deep learning, and the use of big data in order to make automated decisions and to simulate the way that humans learn. Okay, so NLP is a field that lies between these three larger fields. Sometimes we may apply machine learning, sometimes we won't apply machine learning. Today, I'll just show you a really basic application where you would apply a simple machine learning model, but we won't go into the depths of the mathematics or the modeling side of things. Okay, just the pre-processing needed in order to prepare the data for this kind of stuff. So essentially, when we talk about natural language processing, we break the applications down to tasks of natural language understanding and natural language generation. Okay, the terms are pretty self-explanatory. So natural language understanding is the task of understanding text better. So that's either summarizing text or classifying text. You can imagine that this has a wide scope of applications. So let's say, I don't know, social media, you want to summarize comments, if they have some toxic content or not. Actually, companies do this right now. So they classify content on social media based on whether they have any racist or sexist remarks or stuff like that, in order to identify the users that do this, that have this kind of behavior. And you also have natural language generation, which is a bit more complex and a bit more, heavy in terms of computing power and data required in order to do this. And this is the task of generating human language, as you have in autocorrect or machine translation, for example, in Google Translate. So you use things like that on a daily basis, either on your phones with Alexa or Siri, that take your voice, map it onto like a textual representation, and then perform the NLP stuff. Your email does this with spam detection. So spam detection is essentially a classification task where you classify text in spam or non-spam, and you get the corresponding notification. You have Google Translate, which is this natural language translation task. Then you have the predictive typing on the web, which is a form of natural language generation. And you also have document summarization and tons of other applications that I won't describe here, but you can imagine that there's loads of stuff that you could do with NLP. Okay, for this notebook, I'll be sticking to a really basic application of text classification. So we'll take a really big data set of text, and we'll classify it into two classes. So it will be a binary classification task. Specifically, as you can see in this really complex diagram here, we'll take a movie review and classify it to positive or negative. I did this in PowerPoint, so excuse my. And in order to perform this task, we'll be using the IMDb movie review dataset. I'm not sure if you've heard of this dataset before, but it's pretty common in introductory machine learning tasks. So if you go here, this is the dataset on Kaggle, actually. It has 50,000 entries, okay? 50,000 different movie reviews from IMDb. And you have a column which corresponds to the actual review, and then another column that corresponds to the label of the review. So it's either positive or negative. And you have 25,000 entries that have positive reviews and 25,000 entries that have negative reviews. So this is a balanced data set. It's really well formatted, and it's freely available on the web from tons of different sources for you guys to play around. So we'll be using a version that's available on Hugging Face. Hugging Face is a data science community and a company now that develops state-of-the-art natural language processing models. It has tons of data sets and models available here, again, for free. And we'll be using it to get our data from here, okay? So this task of classifying movie reviews is called sentiment analysis, okay? Because we want to predict the sentiment of the review. So if it's positive or negative. In order to do this, we'll need to process the text using some pretty well-established steps that everyone uses. And then you'll see how we can easily apply machine learning to make some simple predictions. So we just start by running this cell. So yeah, it's just looking for a runtime here. Hopefully this won't take long. Okay, so what this is doing, it's just installing this library from Hugging Face, and we'll be able to access the data sets from here, okay? And then in this really big, long, boring cell, I'll be installing every library that I'll use across the notebook. I don't expect you guys to know the libraries. I won't go into really much detail, but it's good to know that Pandas is used for data analytics. I'm pretty sure that in the previous session as well, Valeria showed you a lot of stuff about Pandas. Then we have Matplotlib and Seaborn, which are libraries that are used to generate plots, data visualization, etc. Then we have NLTK, which is actually quite important, okay? So you see that I import tons of stuff from NLTK. NLTK stands for Natural Language Toolkit, okay? And it's a really huge library with tons of tools used for natural language processing. It supports, I think, more than 200 languages for some of its applications. It's extremely useful. It has a lot of different options and a lot of different tools that I'll summarize some of them later on. You can visit the documentation if you want, then you can see that it has tons of stuff that we'll use today, some of them at least. Then we have sklearn. This is the go-to machine learning library for data scientists because it's really low code. It doesn't need you to like code up models from scratch. It gives you everything readily available just with a few lines of code. So we'll be using this. And then finally, we have the rest of the libraries, NumPy, SciPy, etc. I won't go into the details of explaining those. So yeah, I just added a link for NLTK here. If you want to visit the website, it has a really detailed documentation of everything here. You can check this out in your own time. It's built for Python specifically, okay? And it provides really easy to use interfaces. It has several lexical resources, ready data sets. So, yep, it's really helpful. And okay, now let's just start loading our data and preparing it for the machine learning application. So as I said, we'll be using the IMDb dataset here. And the only thing you need to do to load this dataset to Python is use this load dataset function provided by Hugging Face. So remember, I did pip install datasets before, and then I imported load datasets, which is the only function you need to load your data. This will take a while. As you can see here, I just specified that I need the train bit, but you shouldn't worry about this. So the train bit is 25,000 entries long, and then you have a test bit that is also 25,000 entries long. It's a huge data set. For the purposes of this notebook, we won't be needing 50,000 entries because everything will be really slow then. And yeah, I mean, this is just for demonstration, so we won't be needing 50,000 different reviews, but it's there. So if you want, you can load the whole thing. So if we check this thing out, it has a text attribute, which is a huge list of text, which it's loads of movie reviews. And then you have the label as well, which is, again, a huge list of binary labels, 0 for a negative review and 1 for a positive review. So these are just two huge lists, 25,000 entries long, and we need to concatenate the two lists into a pandas data frame. So this is an object that we know how to manipulate. Valeria showed you some basics about pandas. So I do this thing in the cell here. So I just concatenate the two lists. So I zip together the text and the label, okay? If I zip them together, I can print the shape of the data frame. So we have a data frame of shape 25,000 with 2 columns, okay? And the columns here, if I do textdf, I named this textdf, so this will be our dataset name. So the columns of the textdf are text and label. So these are the two lists that we saw before. And we can print a sample of this data in order to have a look at it and understand better how it looks. So if I do sample here, it just prints randomly 5 entries. It samples 5 entries. And I can view it here. So if you can read this, I'm not sure if you can read this from back there, but this is an actual movie review written by someone, by an actual person on IMDb. So it says this independent film was one of the best films at the Tall Grass, whatever festival. Okay. So obviously this is a positive review. The label is 1. Same for the second review. So let's see here, the label is 0. So the review is negative. And I'm pretty sure that if you read this huge review, you'll find out that it was negative. But because we don't want to do this manually, and we are data scientists, we'll write up a machine learning model that will be able to predict these labels without needing to inspect every huge review that someone wrote on IMDb, okay? Next, I can inspect the value counts. So here I say textdf.label and then value count. And what this does for us, it prints the value counts of each unique label that we have in the labels column. So since we have 2 unique values, 0 and 1, we get the corresponding counts for each of those values. So we have 12,500 zero labels and the same for 1. So it's a perfectly balanced data set with half of the reviews being positive and half of the reviews being negative. So we don't have to worry about, balancing the classes and stuff like that. For this notebook, we're just going to worry about the pre-processing steps. Okay, this is the important bit of the notebook. Okay, so okay, let's imagine how we source textual data. We find it from different sources on the web, from Amazon, from Twitter. People write the text, and because people are not perfect, the data is not perfect, and we end up with a huge mess of text, which has different formats. It has spelling mistakes. It has missing stuff. So as in every data set, we need to bring this into a format which is nice and clean, and then we can feed it to a machine learning model. So the first and most important step in natural language processing is pre-processing the text, okay? So as you can imagine, and in every data set, there is some unwanted noise, okay? And depending on the context of the text, this may vary, but like you can imagine that if we have a data set of scientific papers, let's say, the noise would be different than a data set of Facebook comments, because you wouldn't have like mathematical formulas in Facebook comments. Sorry? Depends on the Facebook groups you're in. I mean, in your Facebook feed, I'm pretty sure there are some mathematical formulas. So, but okay, depending on the context, you would do general. So you would do specific pre-processing steps. But in general, there are some steps that are common for every type of data set, and we'll see those general steps here. Okay. So it doesn't matter if it's scientific papers or Twitter posts, we still need to perform these basic steps, okay? So first of all, we have huge long sequences of text. So that's either a paragraph or a review or a sentence, or I don't know, it's a big chunk of text. And we need to break that down into more basic building blocks. Okay, that's called tokenization. So tokenization is the process of breaking down longer sequences to the fundamental building blocks of language. So that's either a word or a subword. In most of the languages, the human spoken languages, we have words, and we need to break text down into words. So this is always the first step. It's not hard to do because, most of the times words are separated by spaces and sentences are separated by full stops. And you could easily code that up and split the text, but some of the times this might be different. So we have the library NLTK to do this for us without needing to, think about each case separately. And then once we break our sentences down into words, we need to remove stop words. So stop words, as I wrote here, are words that do not carry any contextual meaning. So in every language, we have words that are very frequent in the text, but don't carry any meaning at all. So they're just noise, okay? You can imagine that words such as is or the or a are essentially stop words that we don't care about, and we just want to remove them from the text because they just add unwanted noise, okay? So again, depending on the application, the stop words may be different. So in some applications, we might want to keep some words, whereas in some other applications, those same words would be useless. But everyone agrees that there's like a big common list of useless words, and these useless words are defined in every natural language processing library, and you can load it without manually typing each word you want to remove. These lists come in ready formats, and I'll show you in a bit how you can access them, okay? And then finally, we have stemming and lemmatization, okay? And this is essentially the process of normalizing our text, because at the end of the day, you want to map your text into unique representations for each word to be able to represent them numerically, okay? But if you have a huge vocabulary, so a huge data set which has loads of different words, you'd end up having words such as good, better, or best being mapped to unique representation. And you don't want that because good, better, and best have the same semantic meaning. So you need to find a way to represent similar words. So for example, dogs with capital letters with one unique representation, right? So you want to map these similar words to the same unique representation before doing any further steps. And in order to do this, we have two different approaches in natural language processing. So the first one is called stemming, which is the brute force approach of just chopping down letters in order to get a shorter version of similar words, which is common in every word. So for example, in expensive and expense, you just chop down the final letters, ending up with just this thing. That thing does not have any, it doesn't follow any grammar rules, so it's just a chunk of letters. But when the time comes for the computer to read that, it will make sense. So this is a more fast approach. It just chops down letters. There are some algorithms that do this, but it's not grammatically correct. If you want to be grammatically correct, you can use lemmatization, which uses big tables of grammar and some rules depending on the language in order to do this. But as you can imagine, this is much slower. So there's a trade-off between being accurate about your shorter word representations and computational efficiency. Okay, so depending on the task and depending how big your data set is, you would want to decide early on which method you're going to use. So let's see these methods in practice. Yeah, sure.
If we have a comment which is not very good or very bad, where we will classify it? If there is a neutral, for example.
Okay, to be exact, like in most cases, you wouldn't have a binary classification case for like reviews. Most of the times you have more classes, so you'd have neutral, good, bad, or you can even add a score, so how good or how bad it is, with neutral being 0. But as this is a really simple example, we'll just stick to the two classes. But actually, this is a good question.
Okay.
And you can actually assign a score from -1 to 1 in these cases, where 0 is neutral, 1 is the best, and -1 is the worst. So here we just define a stop word list. I just say that I want the English list of stop words. I define my tokenizer, which is a function that splits up the text into words, and then a lemmatizer and a stemmer for each of these methods here, stemming and lemmatization. So this is just the lemmatizer readily available from NLTK, same for the stemmer. You have several different options for these functions depending on the algorithm you want to use or the language you want to use, but these are the established ones that everyone uses. Okay. I just run this, so I defined each one of these methods here. Let's print the stop words and see what we have loaded here. So this is the list of stop words as defined in the NLTK library. So these are all the useless words that the people at NLTK decided to remove from text. So we have a, about, above, after, and it's a really long list of words that do not carry any contextual meaning. Okay, so we want to remove this from our movie reviews because these are just noise. Then I'm just going to show you here what the tokenizer does. So we have this string, just a sample sentence, and we want to tokenize it. So we just do tokenizer to tokenize sample text. And as you see, it's really efficient, really fast, and we split our sentence down to individual words. So this is, etc. Okay. Now let's see our stemming and lemmatization. So the process of trimming words down to their semantic meaning. Here I have defined 3 random words, so traditional, flies, and agrees. As you can imagine, these words can be represented with tradition, fly, and agree. And I'm gonna show you the results of stemming and lemmatization. So what I do here is just call the function stemmer.stem for each word in my sample words, and I'll get the result back. And I'll also measure the time needed to perform this task to compare the two. So if I run this, you can see that stemming resulted in this. So tradit, I don't even know how to read those things. These don't have any grammatic meaning, but I mean, this is what the stemmer did. And it took much less time than the lemmatizer here. The lemmatizer only successfully trimmed down flies to fly because sometimes it also needs the context of the bigger sentence in order to correctly do this. But as you can see here, this was much faster than this. So because we'll be using 25,000 reviews for this example, we'll go with the stemming and see how accurate the results are. Okay. Now I want to formalize these steps here a bit more and put them into some Python functions. I guess that most of you used functions before at some point, but I just define a set of commands that can be applied later on. So here, these are the functions that I'll be using for my pre-processing. So I have this strip HTML function, which essentially removes HTML from the text. So HTML, for those of you that are not familiar, is a set of sometimes weird symbols that can appear in text that was used on the web. So I want to throw away those symbols. I use this library to do it. This is just some standard stuff. So yeah, no need to explain it in depth. Then I have this function called perform regular expressions. Regular expressions are a way of looking for things in text. And once you find them, you can do some operations. So here, I just say I want to substitute everything that's between brackets. So this really weird looking thing means everything that is between brackets. I want to substitute with nothing. So essentially remove everything that is between brackets. And similarly, here I also remove everything that is not text or numbers, okay? So I want to throw away everything that is not text or not numbers. Then I have my stemming function. So here, this is a function that I defined for using the stemmer that I showed before. And this one is used for lemmatization. I'll just use one of the two, and we decided to go with stemming because it's much faster than lemmatization. This is for trimming the words down. And then finally, I defined this function called stop word removal, which removes the useless words. So essentially, I break the text down into sequences of words and check if those words are in the list of stop words, and if they are in the list of stop words, I just remove them. So this complex looking function does exactly this. It just throws away the stop words. And then I call every function together because I want to apply this sequence of commands to my dataset. So I want to remove any HTML, then I want to remove anything that is between brackets, then I want to trim my words down into more simple representations, and then finally, I want to remove the stop word. So this is an example of what is going to happen after editing some random text with these functions. So here I defined this random piece of text called HTML document, whatever. This is something I just found on the web. It's an HTML document. So these are the HTMLs that we want to remove. So these class things and these symbols here, we want to throw them away. So first, I just strip the HTML and print the text. As you can see, it removed all of the useless symbols. Then I perform my regular expressions to remove characters that are not letters or numbers. So I remove this punctuation mark here, and same for other possible things in the text. And then I perform stemming. So I now trimmed down some of the words to more simple representations. As you can see, little became this. We have all of this gibberish that doesn't make sense right now, but it's normalized. Then we can transform this to numbers later on to feed into the machine learning body. And finally, I also remove the stop words. So I remove B, A, etc. So after processing this entire piece of text, I ended up with this short normalized representation. Okay. Now I want to take these functions and apply them to the whole data set. So I do this here. I say that I'm going to create this new column called process text, which is the result of applying my process text function to this column here. So this will take a while because it will apply this function to all of the 25,000 rows of the data set. So if you want to ask any questions now is a good point. I mean, I could have done this with a slightly smaller data set because, as you'll see later on, it doesn't really matter if it's 25,000 entries long. But let's just wait for this. Yeah, as you can see, it's already halfway through. And we should expect it to be done in, I don't know, a few seconds. So as I said, I just apply sequentially this set of functions to each review individually. So strip HTML, then regular expressions, then removal of stop words, and then finally stemming, okay? Individually to each row. And now I'll have a new column, which will be the process text, and I'll be able to compare that to my original text and see what happened there. So it's almost there. Okay, perfect. Now, if I print a sample of the data, we can see here that we have this review. Okay, this is the original text. And then this is the process text next to it. So it removed when, it removed die, it trimmed down, move into this shorter representation. So my functions worked as I wanted them to work, okay? Then I can move on to some analytics now. So here I defined this function called plot word clouds. This essentially will plot visualization of the frequency of the words in my text. Okay, so I just use a library called word cloud to do this. I won't go into the individual lines of this code. This is just for the visual. So I'm gonna plot two word clouds, one for the case where the label is equal to 1. So these are the positive reviews. So I say text df where the label is equal to 1. So this is the case where the reviews are positive. So we're gonna see the most frequent words in the positive reviews right now and see if there's any correlation between, we expect to see words such as good, nice, I guess, and stuff like that. So this is the word cloud for the positive reviews. The bigger words are the words that appear more frequently. and the smaller words are not so frequent, but I can assure you that all of these words that you see here are quite frequent because it's only like 100 words and we have thousands of words in the entire data set. So as you can see here, we have film, we have movie, we have good, we have beautiful, we have things like that, that essentially describe a good movie. Okay, now in the negative reviews, we don't see so many, strong words such as bad or hate or stuff like that. So one could say that, negative reviews are more neutral than positive reviews. And this actually has to do with the question that we had before. So sometimes negative reviews are just neutral reviews, whereas positive reviews are 10-star reviews from someone who really loved the movie. Okay. So again, about the question we had earlier, there's this library called TextBlob, which essentially gives a numerical score to the polarity of each review. So you don't have to do anything. This library just does some math or some averaging techniques, which I'm not sure about. And it gives a numerical score of how good or bad each review is. So at this point, we're not using any machine learning. We're just using some simple libraries in order to see if the results of this function agree with the labels of the fields. So what I do here is I define a new column called polarity. And this is essentially this function textblob.sentiment.polarity. So this is, again, a ready function from a library, which calculates how good or bad a review is. So let's see here. So this is the polarity, this last column here. And we can see that for the negative labels, it's a value close to 0 in the negative value. So values close to 0 are neutral, whereas values smaller than 0 are more negative. So this is just a nice feature that we can use when analyzing text. Again, this doesn't have to do anything with machine learning. It's just a readily available function from a library that we can easily implement and get this numerical representation for the review. So besides the polarity, I'll also add some other columns called word count and character count. Okay, just out of curiosity, I want to see if, for example, there's a correlation between how long is a sentence and how good is the review, or how many characters there are in a sentence and how good is the review. I just want to see if there's any correlation between this stuff. I'm not very optimistic, but we're gonna see. So here I'll just do some descriptive statistics. So I group the dataset by the label, and then I'm printing the mean for each of the polarity, word count, and character count. So we can see for label 0, the polarity is quite small. So the reviews are more neutral, whereas for label 1, we have a slightly bigger polarity, which indicates that indeed these reviews are positive. But of course, everything here is relative because we only used our dataset. So these values are relative to our data. And then we see that the word counts are quite similar for both. The average word counts are similar for both labels. And the average character counts are again similar for both labels. So we don't expect features like this carrying any information, because it's the same across labels. So here, this is just distribution. I'm just plotting the distribution of the polarity. So of those values between -1 and 1. So this is, of course, normally distributed because this text blob function only uses our data, and it always returns normally distributed results. But again, this is not, this is just something extra. I'm just showing you guys an additional library that can be used to calculate the polarity of reviews without using any machine learning, okay? So we won't actually use this as a feature for any machine learning model. And then here, I'll also plot a correlation matrix between label, polarity, word count, and character count. So again, if I do textdf and then core, so this is a function that returns the correlation matrix. And then I can just plot the correlation matrix using some simple commands. So if we zoom out here, this is a bit too big. So this is the correlation matrix here. We see that there's strong positive correlation between the word count and the character count. And there's some correlation between the label and the polarity, but not so strong. This is kind of expected because the polarity has something to do with the label, and the word count and the character count are, of course, directly correlated. Again, this is just out of interest. This is just for exploration. So we won't actually be using this correlation matrix for the machine learning model. Then I also thought that it was a good idea to plot frequencies of each word inside the dataset. So how frequent are the words in the positive reviews, and how frequent are the words in the negative reviews. So I created a function called plot frequencies, which takes in the data frame the name of the column with the text. And here it does some manipulations in order to plot the frequency distribution of the words. So again, this is not something super complex. I just create a list of all the words in my data set here. And then I just calculate the frequency of each word and plot it with some Pythonic commands. But again, this is not the point of the notebook, so I'm just going to show you the results. So here I'm plotting the frequencies for the positive reviews. So I said plot frequencies of the reviews where the label is equal to 1. As you can see here, I have film, movie, good here, great, love. So we have some positive words being quite frequent in the positive reviews, which is kind of expected. These are just the top 25 words in the positive data set. And then we also have the 25 most common words for the negative reviews, which again, you have don't, which is quite negative, you have bad, but again, you have good, you have like. So you can imagine that individual words without context cannot be used to draw conclusions, because besides only the words, you also need to take into account the entire sentence. So for example, good is really frequent in the negative reviews, but you could have a review saying this movie was not very good. So individual words are not, very descriptive of the data itself. Now that we have, found a way to, represent words in a nice and clean manner, we have removed stop words, we have chopped down longer words into more simple representations. We've transformed every word to lowercase. We can move on into representing this data set in a way that can be read by a machine learning model, okay? And what this essentially means is taking those words and transforming them into numbers, because computers cannot read words, they can only read numbers. And there are several ways of doing this, okay? I'm just going to show you one method here, but there are a lot of ways of doing this. So now we are looking for a way to take this huge data set of letters and transforming it into a numerical representation that can be later fed into a machine learning model, okay? So this is a crucial step. You cannot skip this when dealing with natural language datasets because you won't get anywhere without finding a numerical representation for your words. And here we're going to use a method called TF-IDF. It's a really simple method. You can easily understand it intuitively what it does. It stands for term frequency, inverse document frequency model. So as you can guess, it's something to do with the frequency of the words and the frequency they appear across the data set. So we have term frequency and inverse document frequency. These are two separate terms that we'll calculate separately, and then we'll combine them in order to get a numerical representation for each of the words, okay? So term frequency, first of all, as you can guess, is just the frequency of the word in each review. So it is given by how many times a term T, so a word essentially, appears in a document D. The document in this case is the review. And this is divided by the entire number of words in the document. So as you can imagine, a more frequent word, so a word that appears really often, has a larger term frequency score. And as you can imagine, stop words, so words like the or is or a or if, have a really high term frequency score. And this is why we have removed them, because we don't want words that don't carry any contextual meaning having a high score. So this is the first term, and then we have the second term, the IDF, so the inverse document frequency, which is a bit more complex, and this measures how relevant, so how essentially rare a word is in a document. So as I said, when computing the term frequency, okay, as you can see here, all terms are considered equally important, and the more frequent ones have a bigger score. However, we have some words such as stop words that appear very frequently, but they have no importance whatsoever. So in a way, we want to downscale words that appear really frequently and don't have any contextual meaning, and upscale the words that don't appear often, but they have context. So IDF essentially is the inverse of document frequency, and is given by the total number of documents, okay? So the total number of reviews here, divided by the number of reviews with a term in it, okay? And we want to take the logarithm of this expression, because in a huge data set such as ours, where we have 25,000 reviews and thousands of unique words, this quantity here can explode. So we want to take a log, and we also want to smooth the denominator, because sometimes when there are no documents with a specific word in it, we have division by 0, and this causes problems. So we want to add a 1 in order to smooth the results. So with these two terms explained, TF and IDF, the TF-IDF is just their product. So TF times IDF, okay? I know that this might be a bit much to digest, but this has to do only with the frequency of words and how important they are in the context that they appear, okay? And we don't have to code this up from scratch. These terms here can be easily calculated using functions from the relevant libraries, okay? So I'm going to show you how to do this. So how to calculate these terms. First of all, we want to split our data into trained and test sets. So this is a common step in every machine learning application. You want a training set on which you're going to train your machine learning model. So this is the data that is given to the model in order to discover the features, in order to discover relationships. And then you have the test set that is never shown to the model, and it's only used at the end where you want to evaluate your results. So we have to split our data into train and into test. We use this function called train test split from sklearn. I'm sure that you've seen this several times today with Valeria and with Nikos. So we end up with xtrain, which are the words for the train set, xtest, which are the words for the test set, ytrain, which are the labels for the train set, and ytest, which are the labels for the test set. Okay. If we run this and then see how many elements we have in each data set, we can see that we have 20,000 rows in the training set and the remaining 5,000 rows in the test set. Because if you remember, we had 25,000 entries in the beginning. We used 80% for training and 20% for testing. Okay. Now, the data set is split successfully, and we want to take the training set and transform it into numbers. So far, the training set is still a set of words, so of English words, and we want to use the TF-IDF method in order to transform that to a vector of numbers. And once we have transformed the training set, we can use what we learned from the training set and transform the test set as well. So we're going to transform the entire data set using the TF-IDF method, which I defined above. So first step is to transform the training set into a list. Then we feed this list to the TF-IDF vectorizer. Okay. And then we use the vectorizer to transform the training set and the test set. So if I run this, it will take some time, and it will transform my entire data set into a matrix of numbers. So far, we had a set of words. Now we have a matrix of numbers. And if we print the matrix, the shape of this matrix, we can see that in the training set, we have 20,000 rows and 97,000 columns. So imagine that we have so many unique words in our data set because the columns of this matrix are equal to the size of the unique words in our data set. So this is a huge matrix. We won't print this because the whole notebook will crash, but you can imagine that it's really big. Okay. Below, I will. So this is okay. This won't do anything because I only run this if the features are less than 15,000, but here they're bigger than that. So I just wanted to show you guys the matrix here, but use the bigger data sets, so we won't be able to visualize that matrix. But if you try running the notebook with a smaller data set, so only with 1,000 entries, let's say, and you'll have less words, you'll be able to see the data set. I'm just going to show you the words with the top scores, okay, with the top TF-IDF scores. So if I print the scores here, these are the top scoring words again. So this is the sum of all the scores calculated by TF-IDF. So the top words, so the most context-related words in the whole data set are these words. So movie, like, watch, good, time, character, etc. So essentially TF-IDF worked correctly because we can see that the most relevant words in the data set are indeed words that are relevant to movies and relevant to reviews, okay? And if we print the final 20 words, so the worst performing words, we have some random gibberish here. I don't even know what these things mean. So you have these random words, and these do not carry any context whatsoever. So using the TF-IDF, you can give these numerical scores to individual words, with words that are more relevant to our context having much higher score, and words that are not relevant being much lower in terms of score. Now we're at a point where we represented our entire data set using only numbers. And the last step is to feed our machine learning model to those numbers, make some predictions, and then we're done, essentially. So there are only a few lines of code left here. If you have any questions, please ask. I'm just going to use a logistic regression classifier in order to make my predictions. So again, this is a binary classification task. So we want to predict if a review is positive or a review is negative. To do so, we need a classification model, specifically a binary classification model. So logistic regression is a really simple classification model. You can see a really nice introduction here of the logistic regression. I won't go into the details. Most of you already know what a logistic regression function does. So I'm going to take this logistic regression model and feed it to my training features. So the numbers that I've got from my training set, okay, which has size 20,000 times 97,000, blah, blah, blah. So this is that huge matrix I've showed you before, the entire matrix of TF-IDF features extracted from the training. So I feed that to my data. It will take a few moments. Okay, now I gave it my training data and I'm ready to make some predictions. Okay. Again, this is a binary classification task, and in order to evaluate binary classifiers, we use a confusion matrix. Valeria talked about this a lot during her presentation. So as you know, in a confusion matrix, we quantify how many of the predictions on the test set were correct. And to do this, we use quantities such as the true positives, false positives, true negatives, and false negatives. So you guys already know what these are. So the true positives are the positive reviews that were indeed classified as positive. The false positives are the negative reviews that were classified as positive, etc. Okay, and from these quantities, we can derive scores such as precision, recall, accuracy, and the F1 score. Remember that this is a perfectly balanced data set, so half of the labels were positive and half of the labels were negative. So accuracy will be just fine for classifying our model here because the classes are balanced, okay? So here, this long line of commands essentially makes a prediction on the test set. See features test transformed. So this is the matrix of the test TF-IDF scores. Then I plot a confusion matrix, okay? And I record the scores here. So this is my confusion matrix. Accuracy of 89% almost, F1 score same, really good metrics here. I'm just gonna plot this in a more nice way for you to see. So indeed we have here are negative reviews. Most of them were correctly classified, same for the positive reviews, and just a small set of wrong predictions. So just with a simple logistic regression model and some simple preprocessing, we achieved a really good performance on the test set, namely 89% accuracy, okay? And finally, now I have my trained model, everything is ready, okay? I've seen that the model does really well on the test set, so in reviews that it never saw before. So I thought it would be a good idea to go on the web, okay, and find some random movie reviews that were not in the data set that we used. So that weren't a part of the 25,000 reviews that we used in this notebook. So I found 2 reviews from IMDb here. Okay, these are 2 real reviews that I found last week on IMDb for this new movie called, okay, it's not new, it's it's remade, All Quiet on the Western Front. It's a recent release, so it was just released a month ago. These reviews were added a few days ago, so these are reviews that our model hasn't seen before, and we're going to test how it performs and what predictions it makes on these reviews. So this is the first one, is my negative review. Okay, hopefully the model will correctly predict that this review is negative if you want to read it. This is a 4-star negative review, and this is a 10-star positive review. Okay, so again, I found these on Google a few days ago. And I just defined this function called make prediction, where I take some random text as input. I process it. I need to process it in exactly the same way that I processed the rest of the data. So remove the stop words, trim the words down, tokenize, etc. So that list of functions that I showed you before. So I need to pass my text through that list of functions. Then I need to transform the result into a numerical representation using my TF-IDF method that I showed before. This vectorizer is already trained on the training set, so it knows how to transform each of these words. So it knows what score to give to each of these words because most probably it has seen them before. Okay, and then I just give the text to my trained machine learning model and I make the prediction. Okay, so I just call this function make prediction on my positive review. And if I run this, this is the processed text. So this is the result after feeding the text into the process. This text here, the positive text. After feeding the text to the processing function, I get this gibberish here. And then I also get that this review is positive. So it correctly classified the positive review. And if I do the same for the negative review, again, I get the processed version of it. Okay. And then I also get the correct class. So my model works perfectly well for these extreme reviews. Of course, if I found something more neutral, the results would have been maybe wrong, but for these 2 reviews, it worked just fine. So yeah, this is the end of the notebook. We finished a bit earlier. If you have any questions, please ask.
Maybe I can ask one.
Sure.
So I just look at this, that you have predicted something that that you just look from the internet. So my thought is that maybe the words that is there in this review, most of the words are just the words that are going to have I don't know if TF-ID, I don't know if I pronounced it correctly. So I'm just thinking that if we are going to pick a review from the internet again, which is and most of the words in this review is having the lower TF-ID. Will it have the same prediction like positive or negative review?
So, okay, we're hoping. Now we gave it a pretty big data set to train on, right? So 25,000 reviews, and we had something like 97,000 unique words in that data. So 97,000 words are a lot, and we have a score for all of those. We have a TF-IDF number for all of these words. So if we have a new review, most probably all of the words in the new review will have a mapping in the TF-IDF. So we'll have a score for those.
Suppose we have a review whereby the words are completely different from what is in the training.
If the words are completely different, they won't get a correct score. So I think they'll get a 0 or something like that.
Okay.
And there the review will be, the prediction will not be good And thanks for your question, actually, because if for example, I give it an Amazon review, not a movie review, most probably most of the words won't be in the data set. But that's a data point that is outside of our distribution. So it's from another distribution. So the model will not perform correctly. But the TF-IDF is just one method of turning words into vectors. Now we have much more advanced methods. So for example, there are some huge matrices called word embeddings, which you can download, which essentially were created using the entire text from Wikipedia. So imagine that billions of entries, and using that huge data set, they created this huge matrix that has relationships between words and context also. So if, for example, you have a new word, you just pass it through that matrix, you map it to the correct representation, and you get the number you want. So this is the new state-of-the-art method now to translate words into numbers. You get these ready matrices from these libraries, so you can download them. They're huge. They have billions of parameters, and you map your words to the matrix.
Okay, thank you. So I'm also thinking that, so you just mentioned that maybe you can, there's this idea of trying to capture the old words from the Wikipedia, but my thought is that sometimes the word that you're using for movie, for example, is not an English word or something literal English that you can find in Wikipedia. So maybe something completely out of Wikipedia. So most probably also there will be some error in terms of prediction, I guess.
Yes, so most of the times you try to cover this case by either remove, so you have most of the times when you map the words to numerical representations, you also have one representation for words that you've never seen before. And every new word, which you hope is not very common, you map to that. So let's say we have a number that is specifically for words that we haven't seen before. We hope that those words don't appear very often because we use a huge data set to train our model. But if they do ever appear, let's hope that we can find context from the remaining sentence.
Okay, thank you.
Thanks. Any other questions? Okay.
Any questions else? See online? No. Okay, in which case, thank you very much, Nicolas. Thank you for joining online. Thank you for coming here today. The sessions will be online later on in the afternoon or maybe tomorrow morning. Check them out if you want. Also check out our previous training events. There's more advanced sessions in data science and in everything else that was taught over the past 2 days. I think Nicolas had a session in the previous training events as well, intermediate session, so you can check that out. Again, thank you all, and goodbye for now.